Okay, hi everyone. The next presentation will be given by Dr. Peyam Tabrizian from Brown University, and we'll be talking about using visuals to enhance students' love for differential equations.
All right, thanks so much for having me. And since it is Valentine's Day, I decided to slightly rename my talk to say using visuals to enhance students' love for differential equations. And let me start by telling you a little story. So back when I was a senior in college, a while back, I took an astronomy class where the instructor showed beautiful pictures of planets and wooed all the students with those amazing visuals. And I was a bit jealous, to be honest, because I was like, ah, I wish math had that, where you can just show beautiful pictures and students will be amazed. And in fact, that is what my talk is all about. Namely, I want to show you the beauty of visuals in differential equations classes. And again, not just to woo the students and attract students to differential equations, but also in an educational perspective to help them understand how differential equations work. And so for today's talk, I put them in 5 categories of visuals. So in the first lecture, when I introduced the students to differential equations, I first showed them this Reddit app that I found that illustrates very nice flows of differential equations, which I want to share with you. So this, and I think it's part of some program that shows vector fields and flows. A neat one. So that is one thing, which I can look at those beautiful flows. And then I can show you just a couple more. Like this one was very wishy-washy. Let me see. And then there are a couple of other ones that I want to show. Oh yeah, Mandelbrot set. Also a little bit of fractal differential equations. And again, all with the purpose of showing students, really introducing them to how beautiful differential equations can be. I think there was another one, yeah, circle convergence, which is also very beautiful. And again, I'd be happy to share the slides with you with the link as well. Okay, so that is one kind of visual. Let me see if I can go back to the presentation. Yes. And again, the purpose of this, it's really great for a first lecture on differential equations. It gives a very nice illustration of what flows are. And by the way, in case you're teaching multivariable calculus, you can also use the same applet to show or illustrate vector fields when you start your chapter on vector fields, because again, vector fields also induce flows of differential equations. Okay. Now that's one thing. Then, and this is a bit in chronological order of a differential equations course. Then, when I cover direction fields, there's a really cool app called the D-Field app that's super accessible. And what it does, it plots direction fields of first order ODEs of the form y prime equals f of y comma t. And I also show you nice pictures. And what I like about this, it's very easy to use. So you just go on a link and you don't really need to know any programming. And it's also great for explaining the logistic equation, which I'll show you. In fact, I want to illustrate a couple of things with this app. So this is the D-Field app, in case you're not familiar. And literally the only thing you have to modify in this app is your differential equation. So here it illustrates, for example, y prime equals sine of t times cosine of y, and it plots direction fields, and you can even click on sample solutions. And again, no programming experience required whatsoever. The student can just go to this website and plot things. And as I mentioned, it's really a great illustration of the logistic equation. for instance, here I illustrate, for instance, let me change this a little bit. Y prime equals 3 times y times 1 minus y over 4. And you can really see that there's two equilibrium solutions here, if I can click on them correctly, but also the solutions in between, namely the one that increase up to the carrying capacity. And also, in case you're looking at negative solutions, they go down. And also, if you're above the carrying capacity, you can see that the solutions then converge to the carrying capacity. Again, a very easy to use and nice illustration of direction fields. So that is one kind of applet. That's one thing. And then let me see. Again, thank you for sharing the link as well for the default app. Now, the next couple of applications I want to illustrate are some Desmos visuals, which I created myself. And again, I'd be super happy to share them with you. And again, what's nice about Desmos is you can get creative. Yeah, any questions? And again, I want to show you a couple of cool ones that I created. One is for the Laplace transform because students have a difficult time visualizing this. So here's my attempt to show them the Laplace transform. And in fact, what I want to illustrate is what happened to the Laplace transform of cosine of t. So what happens here, if you prove the formula, the Laplace transform is s over s squared plus 1. And the feature about s over s squared plus 1 is that it increases and then slowly decreases. So just remember this. It increases and then slowly decreases. And that's what I want to show you now in this applet that I created. So once again, let's say we have cosine. So cosine times x of minus sx. Y is a Laplace transform. And the value of the Laplace transform will be the blue line, which I'll show you now. And once again, remember, it's supposed to increase and then decrease. And you'll see this will happen exactly to the blue line. See, the blue line is going up, which shows you the cancellation of the area, and then slowly is going down, which again illustrates the Laplace transform as a weighted area. So I just want to show this again to you. So it's supposed to go up because the red area cancels with the violet area, and then it goes going down. Now, this is for differential equations. I do also want to mention that there's a similar applet I created for the Fourier transform in case you're teaching partial differential equations. So here, the Fourier transform of the Gaussian, the beautiful fact is that it is Gaussian. So it goes up and down. And this applet also shows this. So here, again, I just illustrated with the real part. But once again, the blue line goes up and down. Actually, let me do that. So you will see suddenly the blue line will go up and down because the areas cancel. And then let's see, whoosh. Yes, so now it appears, goes up, and then goes down. Which again is this nice illustration of the Fourier transform really as a cancellation of areas. So we have that. Then Dirac delta. So just a very nice demo that the students can use to see that the Dirac delta is a limit of multipliers. So it's a nice applet that students can just use it to slowly illustrate this. And also the wave equation, so a nice picture of waves. Okay, that's more for partial differential equations. And the Pluckett string, which I won't illustrate here. But also another thing, so when you teach differential equations model for COVID, and in particular you deal with transition fronts, one common confusion that students have is when you see this curve, it looks like it's increasing. So in the COVID model means people are getting more infected, but I actually want to show them that the opposite is true, that as the transition front passes, you actually get less and less infected. And the way I illustrate it is if you're here, then the value of the function is the maximum level, meaning you're infected. But then as time goes by, the value of the infection where you are actually decreases. So you actually go from the value of 4 to the value of 0. So even though this curve is increasing, it's actually decreasing in time, which is a common confusion that students have. Now, those are my own visuals, but I also want to show you that there are really cool applets that you can use and that can be found online. So, for instance, if you're teaching about masses and springs for second order ODEs, I found this really cool applet where you can actually put masses on springs. So this is also super cool. So this is a mass, and look how it swings. It's kind of cool. And there's also many different parameters that you can change. For instance, you can have gravity, like swinging on the moon. You can have the spring constant changing. Let's see here. Think like a rusty belt. And also, you can also add damping when you click on this lab function, which again, you have masses and springs. And suddenly, if you change it to lots of damping, you can see that eventually the masses and springs stop, or at least become infinitesimal. So masses of springs, and then convolution, which confuses a lot of students. So convolution, again, integral from 0 to t of some function and then another function moving to the right, which again, I explain as a weighted average of two functions where one moves to the right. And this applet illustrates it quite nicely because the question is, what is the convolution of this triangle and this square? If you animate this, then notice the square is moving to the right, and then you have this weighted average, which sort of becomes like a bell curve. So let me animate this again. You see this weighted average when moving to the right. So convolution, and also actually I will do this on Wednesday after the break. So we'll start our chapter on second order ODEs where there are two parameters. And a nice application of this that I always illustrate is with the game Angry Birds, which again, I have it saved here. Because Angry Birds, the way it works is you do have two parameters. You have an angle and the direction of the force. So think like initial position and initial velocity. See, you can modify the angle of the bird and how much it swings. And really, to solve Angry Birds, you also just have to ask, is there a trajectory or is there a bird that goes to a certain peak? So is there a trajectory here? Yes. Which also nicely explains existence uniqueness, because non-uniqueness would mean the bird splits into two, and then non-existence would mean the bird blows up, which are two really cool features, I have to say. Okay, and then let me see. So Angry Birds. And then there are other cool demos. One is illustrating the heat equation and then the wave equation that I feel free to check it out. And the last thing I want to illustrate is when you do systems of differential equations, there's a similar app to D-Field that's called the P-plane app that also plots phase portraits. And it's great for systems of ODEs, like x prime equals something, y prime equals something. And once again, the nice feature is it is easy to use. It does not require any programming. And in fact, I want to show you a couple of examples. So let's say 2 times x times minus 3 times y, and then 5 times x minus 7 times y. And the nice thing is it graphs sample curves. Maybe let me make this a bit nicer. This, yeah. For instance, here it graphs. It it illustrates sample phase portraits. That's what I'm saying. So here we have something hyperbolic going on. And of course, the nice thing is you can get very creative with this. And in fact, in this last part of the talk, I want to show you some really cool pictures of this. So in a segment I like to call Peyam, which is also my Instagram name. But for instance, you have this equation x prime is minus half x plus y, y prime equals sine of x, which gives you the following phase portrait, which might be reminiscent of another famous painting you know, which is the Starry Night. So I always believe Van Gogh was a closeted mathematician. So maybe he loved differential equations so much he was inspired by them. But the cool thing is you can also modify this to get more whirlpools just by changing sine of x to sine of 5x. And then another one I like is the wishy-washy ODE. This one, where notice there is this nice change of orientation. So every basin has a different orientation. And my favorite example, which is called the harmonic oscillator, and I always tell the students that was the example that got me hooked on ODEs. Because if you take this decoupled system, the nice thing is you have a closed curve. And the question is, what happens if you change the parameters? What happens if you change a 4 to a 9? In this case, you still get a closed curve. What happens if you change a 4 to a 25? You still get a closed curve. Now, notice here, the reason this works is that the square root, like the ratio of the frequencies is rational. The question is, what if it's not? Let's take this system where square root of 2 over 3 is irrational. Then, at first it looks okay. But then, what happens as time goes on? Whoa, you get this crazy thing. What happens if we move on more? Suddenly it fills the square, which is so crazy because if you just change your frequencies a little bit to make it irrational, suddenly you get from this closed periodic curve to just filling the square. Which I thought that was so cool. And again, it got me hooked to ODs because, again, of all those beautiful pictures. And of course, then I illustrate this is the first example of chaos. And then I talk about the Lorentz system, where there was this mathematician, Lorentz, who tried to predict the weather and then predicted chaos. And then similar, I talk about a project I did during undergrad about a homoclinic orbit, which is just a self-intersection of kind of hyperbolic, of attracting and a repulsive curve. And the question was basically that I studied is, what if you have two homoclinic points, then we get chaos. Now, I did save the best for last in the last minute because I had a student who was part of Brown University and the Rhode Island School of Design, and she was so inspired by this that actually she created sketches based on the Lorentz system. So again, Zoe Goldenberg studied art and applied math, and then did fashion on Lorentz systems. And I want to show you the sketches. They're so cool. So for instance, this, there are more sketches. Again, all fashion sketches. And again, look a bit how chaotic this looks. This, this. And the cool thing is every time I email her, she had another update because it turns out she then used those sketches to actually create fashion designs. So here's the outfit that she then created. And it's really a sportis and skirt inspired by Lorentz attractors and modeling chaos through order operations. And the way she used it, she used only rectangular patterns with curly linear overlays to create an ordered system of creation, like periodic curves in the Lorentz system. And you may ask, what is she doing now? Then she just went on to work to NASA to design spacesuits, which is like the coolest thing ever. Yeah. All right. And again, just a little shameless plug. If you like this, make sure to subscribe to my YouTube channel that has over 180,000 subscribers. And again, thank you for listening to my TED Talk. I really appreciate it.